Hello, I think you know who I am, and I think you all know who Payman is, and this is another episode of Machine Learning and Data Mining. Today we'll talk a little bit about the fundamentals of learning, and it's still fall 2020. Don't forget that assignment 1 is due Friday. You should pretty much be almost done. If you're not, hustle up, and don't forget about the course webpage. The last time we talked about supervised learning notation, we established a notation where X is the feature matrix, which consists of n examples or samples of D features, and we did the allergy example all along. And Y is a column vector of class labels, in this particular case, 0, 1 labels, as in sick or not. And we established a notation for indexing into X either by individual data item or by the set of features for a particular example, or the column of the feature matrix for a particular feature, and so on and so forth. And we've been talking about this food allergy example, but of course it's just one teeny tiny, like kind of silly motivating example for a much broader endeavor, which is supervised learning, right? We can use supervised learning basically to learn any kind of input-output mapping, from email spam filtering, from features of emails to whether or not it's spam, from images of characters to their digit or character class, from picture contents to who's the picture of or what is the picture of, tumors and medical images, so on and so forth. Basically, you can frame a very large number of things as supervised learning. And in fact, thanks to what's it called, self-supervision and these sorts of things, you can actually frame even a broader set of things in terms of supervised learning by basically making up supervision signal. Today, we're really going to be talking about things like generalization error and overfitting and test error and approximation error and these kinds of general concepts. But the way we'll build towards that today is that we'll think about another specific example, and we'll think about what it means to sort of like learn a really good model and what are the consequences of learning a really good model. So the model family that we're going to talk about is the only one that we have, which is decision trees. So we're going to think about that right now, although the concepts we talk about today are going to be related to concepts that we cover and think about further on in the course. So let's choose a different application. So it's another supervised learning application. It's not the allergy example, but let's say that we want to figure out which city it is out of San Francisco or New York. So this is going to be, +1, -1, or whatever. These are going to be our labels, right? And we have a bunch of features. We have 6 features here: elevation, the elevation of the home, the year it was built, the number of bathrooms it has, the number of bedrooms it has, the price of the home, the number of square feet in the home, or square meters, depending on what you like to think in. And we want to build a classifier from these xi's to these y's, something like that. Okay, cool. So we talked about exploratory data analysis and plotting all sorts of stuff and scatter plot arrays and these sorts of things. But let's actually build a model. And you can be thinking about this is really either we're talking about the model. It doesn't really matter how we fit the model or how we learn the model or whatever, right? But it's going to be a decision tree, and let's think about what it means for the model to get better and better. So we can plot, for instance, elevation. And if we wanted to learn a decision stump on this, I learned that I can zoom, which is kind of nice, right? So here is 227 feet. That's the maximum elevation in this particular city. There's 73 feet maximum elevation in another city. And if you're familiar with or have visited either New York or San Francisco, it's pretty clear that the lower ones are New York, and San Francisco actually has some hills, right? Quake Tower, that sort of thing, right? Petrera. So if you build, that's not a very good line, a decision stump based on splitting on elevation at the dividing line 73, and then you can split up this data set fairly well, separating off these homes and assigning them to San Francisco, and then leaving the remaining homes still a little bit messed up. So this is probably not going to do a very good job. It's not the best classifier that you could have based on the feature set. Another thing you could do is go in and look at all of the features plotted in relation to the other. This is the scatter plot array that we talked about. So up here in the upper left is the home elevation versus the year it was built, and of course the greens and blues are New York and San Francisco, but we wouldn't necessarily, but we have that. But what we want to do is we might want to find, again, you can think about what the greedy selection algorithm is doing is going through and trying to figure out which ones of these are going to be the best things to split on. Or manually, if you were to build the decision tree, you would go in and look at this and you'd zoom around and say, bathrooms versus bedrooms, if I want to split on a horizontal or vertical axis, is probably not the best thing to look at. Price versus square foot, it's clearly separable, but that's not the kind of decision rule we know how to put in there. Price per square foot versus price, that's kind of a weird thing to look at, but maybe there's a decision rule you could put here. But if you go up here to price per square foot and elevation, that one is, you can imagine you'd do a pretty good job splitting on that, right? So if we, plot the elevation and price per square foot, you could build a reasonable, a better than a single stump decision tree classifier with the following tree. And apparently people can see the green and blue squares here. I can't see them on my own monitor, so it's a little bit hard to know for sure. There's a green square here, and there's a blue square here, and that corresponds to this particular relatively small decision tree where we first split on elevation, above 73, below 73, right? And then we split on price per square foot, above and below. And this does a pretty good job. It is a better classifier. It's a better model of the data than what we had before, but we still have this to deal with, right? So we have basically near perfect accuracy in this region. We have near perfect accuracy in this region, but we still have to do some more splitting down here if we really want to have a good model, right? So we know how to build this automatically, manually, so on and so forth. But and some people mentioned this in the last lecture and started to ask questions about this, which is great, right? The question is like, what happens to the tree as it gets deeper, as you start adding, like how does the depth of the tree affect accuracy, right? Okay. And really what you should be thinking about in your head is like, how does this affect accuracy on unseen feature vectors, right? Like, okay, you get a new data entry from MLS or whatever, like how's it gonna do? So I don't think I have to zoom this one, right? So this is the original elevation, but the point is if you choose a split here, right, we can now sort of visualize so basically all the data items over here are going to get shoved down this side, and all the data items over here are going to get shoved down this side. And you can visualize the entropy of the resulting splits by noticing that this is very ordered, right? In other words, most everything over here is San Francisco. So this is good, but this over here is not terribly ordered. It's a high entropy distribution, right? As there's pretty even splits, right? So if we then go and do the recursive splitting that we talked about last time, where we've split here and that divides the data set, and we split here, this divides the data set again. Note, somebody asked in the last time I lectured this, that you don't have to, I don't really care about the size of the circles, but that's like the relative fraction of points that go down into that circle or something like that. The point is we're going to keep doing these splits, and we already sort of established, but we just want to drive home the point that as you keep splitting up space into finer and finer subregions, the purity of the labels in these subregions starts to get higher and higher. They get more and more pure, to a point that if you think about it, like this is some very, very high dimensional, we can't really draw, apparently I can't even draw a three-dimensional space, but it's some very high dimensional space, and you start cutting this space, you cut it here, so there's two two subspaces here, and then you cut it again on this subspace, and there's now, 4 subspaces and so on and so forth. You keep cutting this 6-dimensional space using these things where you're actually just, cutting some, if this is the upper region that we just established, then you're, cutting this in this kind of a way. So the point is, you're cutting up this high dimensional space. That I can see that didn't make any sense. The point, what I was saying is that you're doing like half plane split. So once you split here, you can also split here, and then you can split here, and you can split here. So you can identify this region by splitting subspaces. All the splits don't go all the way across the entire space. That's what I was trying to draw, but totally unsuccessfully. Anyway, this resulting set of leaves you can think about as regions in very high dimensional space, right? Sub-regions, right? That have been established by cutting with half planes, right? Cool. Obviously, if you cut up space enough, then the number of data points that in those subregions of space could be 1, right? Or certainly you could cut it enough that that every possible test data point is classified perfectly, right? But let's think about, just for a second before we go on, let's think about what happens if we cut this further and further and further, and there's a positive point here, and there's a negative point here, right? What is the decision boundary, right? Like where, is this really, are the subregions of space exactly where they need to be, right? Is this really actually a good model, right? And this is what we want to think about, and this is what we're going to think about today, basically, right? So with a really deep decision tree where we've split every single subregion such that the entropy of the resulting labels in each of the leaves is 0, right? With this decision tree, the training accuracy is 1, right? We correctly classify every single training instance, right? But as a thought experiment, right, what would happen if we then got features for 217 other houses that were not in our training data, right? Okay. So what is this training accuracy, which is perfect, we perfectly classify everything, tell us anything? What does it tell us about our test accuracy? How are we going to do on the 217 new home features, right? In other words, how does it do on data not used to actually make the tree? How does it do on data that wasn't used to train the model? And in this particular case, it doesn't do perfectly, right? In fact, the test accuracy goes down, right? So clearly there's some disconnect between training accuracy and test accuracy, right? And this is going to be sort of the generalization error, right? In general, this is introducing a term that we'll use a fair amount, right? If you make your model too complex, which is to say, in the decision tree case, it has many, many, many branches, right? And correspondingly many leaves, right? Often this will lead to a phenomenon that we'll refer to colloquially, it's a technical phenomenon, but we'll refer to it colloquially as overfitting, right? And overfitting is just basically achieving lower accuracy on new data than you think you should based on various signals you have. The signal we have available to us right now is training accuracy. So if you have perfect training accuracy, you might think, hey, I'm done. It's going to work awesome in the real world. But in fact, actually, it may not, depending on whether or not you've chosen a model family that's too complex, right? So in the decision tree case, the rules that we induce or train or learn or whatever would be too specific to our exact training data set if the tree is particularly deep. So relating this to our coupon collecting problem, right, where we divided up the United States of America. Oh, that's a lovely map, right? And we collected statistics about individuals in each state, right? If we didn't have enough individuals in each state, we couldn't compute their mean height or we couldn't compute population statistics of the individual components, right? But the point is that's exactly what we were talking about before. Really, the states are just a subdivision of a two-dimensional space, and we have a population of samples running on top of those. The tree structure that we're talking about is just a subdivision of a high-dimensional space. And in order to make statements about specific small subvolumes of this space, or even more to the point where those divisions should be, you need to have more than a few samples in each of those leaves, right? In order to make, in order to be relatively certain that the predictions that you make are decent, or will perform well in test error, since that noise was not from this, right? Okay, great. Okay, so we're familiar with supervised learning notation at this point. We're given training data where we know the labels, right? But now we're going to introduce a new concept, right? And there's actually a little bit of, there's some room for confusion even here. So there's testing data, and there's going to be a testing data set that we're going to talk about. Mostly we're going to be talking about a testing data set, and there's actually test data. And this distinction is relatively important. Let's do it like an industrial setting, right? You're going to have some training data, and then you're going to keep around or separate from that training data some test data that you use to predict how well your system will work when you actually put it out in the real world and people start providing data to your service or sticking data into your service, and you have no idea what the labels are, you have no idea how it performs, nothing like that. Does that make sense?
I have a question. So is there any way to know how deep your tree is supposed to be, like when to stop?
This is an awesome question. I'm sure many people are thinking it. So thank you for simulating the how many people are on today? 98. Well, I got to 98. 98 lecture participants. So we will discuss mechanisms for deciding how many levels to have in the tree. Let's just say we're going to talk about the beginnings of the underpinning of how to understand how to do that today. Generally speaking, the depth of the tree we'll refer to as a hyperparameter, which is fine. We'll talk about that today. And that we'll use something like cross-validation and model selection under cross-validation to select the depth of the tree. Yeah, okay, so there's a distinction, sorry, and I just want to make sure that we're relatively clear about this, although it's a little, we're only really going to talk about test data here, right? So if you're building an image classifier, right? This image has a picture of, I don't know, a copyrighted image in it, right? Like, it's got Mickey Mouse in it, whatever, right? And we want to classify images that are on the internet as to whether or not they have this copyrighted material in it, right? So you're going to build this crazy system internally, and you're going to have training data to set it up, and we're going to talk about validation data and test data internally, but right now we're talking about test data. So you're going to have some test data, right, internally, where you actually know the labels, right? But then you're going to make an Amazon, web service, what are they, the SageMaker web service, and people are going to start shoving images through it, right? You don't know whether or not they have Mickey Mouse in it or not, right? So there's actually test data. There's actually the stuff that's actually going to be run through your system, which you never have labels for and you want to do well on, right? And we're going to have right now, data we have where we know the labels, and that's going to be our test data. And the test data internally, we're going to pretend that we don't know the labels for. That's going to be Y total, right? So we're going to pretend that we don't know the labels for them. And what's about to come is that we're not going to actually ever be able to look at these test labels get screwed up, right? So supervised learning typically consists of a couple of steps, right? So we build a model based on the training data, right? That we'll refer to as the training phase, right? We've talked about how to train a decision tree so far. That's it, right? And then the model, we'll use the model to make predictions on test data, right? So the question is really, instead of training error, we want to consider the test error. Like, are the predictions y hat similar to the true unseen labels y total, right? And this is actually the real goal of machine learning. Like, we don't care about training accuracy at all, right? You know, every once in a while we look at training accuracy to make sure that it's going down and we're not totally screwing up and so on and so forth, right? While we're training models. But what we actually care about is test error. We care about predictive performance, right? And this is, again, I've sort of mentioned this a couple of times as a distinction between machine learning and statistics, right? Yeah.
What's the difference between test error and test set error?
I think, Gideon, thanks. I think this is one is computable. In other words, you are going to retain a test set and you can actually compute the test set error. The test error would be the expected error over all data that you could ever see. You can never actually compute this thing because you never actually have access to the label. So the test error is something that we actually don't have a handle on, right? We can never have a handle on, right? So, but that's actually the thing we care about. So that makes it a little bit complicated. We care about the test error. We care about how it works when we actually deploy the service on SageMaker or whatever, right? But how could we ever know? Because we're never going to actually have the labels. We're going to be generating the labels in that case, right? So, like an analogy that we've used for a number of years in the course about like this distinction between like training and test error, right? So if you all are starting to worry about the midterm, right? Maybe you have some access to some practice midterms and you work on those and so on and so forth, and you try to minimize your training error on those midterms, like you work really, really hard, right? And then you actually go off and take the midterm. The test error is the actual midterm. You don't have the answers, you don't know what grade you're going to get, so on and so forth, until you actually do it. The goal is, of course, to do well on the actual midterm, not the practice one. And of course, this actually brings up exactly kind of the point of machine learning and like the point of the main point of what we're talking about in terms of overfitting, right? You can always just memorize your training data. That is a model, right? But that's not learning, right? I mean, it's a form of learning, but it's not the learning, right? You can like I said, you can, perfect accuracy, just memorize your training data, right? But you've actually only learned if you can generalize. You can do well in new situations, so that you can do well classifying or regressing given new features, right? I see a question here that's a little bit early. Like, what's the ratio between test and training? This is beyond where we're at right now, so we won't worry about that. And that, generally speaking, there's actually really only rules of thumb for this. So, but more important right now is to establish maybe the number one most important rule in machine learning, the golden rule of machine learning, as it were. Even though what we care about is the test error, right? That's the thing that we want to optimize our performance on. The test data that we have, right, cannot influence the training phase in any way. You cannot use test data when you're training your model. It's an absolute no-no, right? We'll measure test error to see how well we do on new data, but if we use the test error during training, this measurement of the test error does not serve as an unbiased prediction of how we'll do on true test data, stuff that we actually don't have the labels for. You can basically start to overfit, like if you start to use it during training, and to extend the midterm analogy, it's like cheating on the test. And this actually shows up and has shown up in various guises in the real world. This is one of these tan slides. You don't have to know this necessarily. The golden rule of machine learning, like even though what we care about is test error, you cannot influence your training phase in any way. So, right, what if you happen to be a large, major international machine learning company? Maybe you heard about this. It happened in 2015, so it's kind of interesting, right? And you are participating in a public classification challenge, and there's a server that allows you to evaluate your performance on a test set, right? What if the design of the competition allowed you to query that 10,000 times, 100,000 times, however many times you want to, right? This would lead you to, if you do things the right way, to develop a model that works very, very well on that particular test set. But then that would not necessarily generalize well. So you can win the competition, but it wouldn't necessarily actually be indicative of a model that generalizes well, right? So this is actually how Baidu cheated and won one of the initial image classification competitions, right? You also can't change your test set, right? That's clearly like verboten, right? But this actually happens as well, right? You can't, change your test set to get the result you want. And this is actually related to a crisis in modern frequentist statistics, where one of the very common things that happens in traditional frequentist statistical methodological studies is that you'll collect some set of data and then perform a large number of hypothesis tests, reporting only those hypothesis tests that return some significance, a result with some significance level. But this is basically like using your test data over and over and over again, because you have one data set and you're testing multiple hypotheses on the data set and returning only those that are significant. That's a very, very, very not good thing to do, and it happens all over the place, right? So if you want to modify your hypotheses, in other words, if you want to test some different hypothesis in the standard frequentist sense, right, you actually need to test on new data. You have to actually go collect new data and then test, and that then is an unbiased estimate of this. And there's a huge literature on this that, if you're bored and don't have enough to do already, I recommend that you go take a look at. If there are any budding learning theorists, and I don't know that UBC has any particular strength in learning theory, although we have a new faculty that knows a fair amount about it. It's not my strength, but if you're a learning theorist, you might confront yourself, or pretty quickly be confronted with this kind of depressing notion, which is like, is learning possible, right? How could we possibly learn, right? Does the training error say anything about the test error, right? And the depressing answer is, in general, no, actually it doesn't, right? The test data can have nothing to do with the training data. And a perfect example of this is when you do just label switching, right? So if, for instance, here's my training data set, right? And my test data set, I'm gonna be a total bad person, right? And I'm gonna give you, as your test data set, the exact same data, but with all the labels switched, right? So you can drive your training loss to 0 if you want to, but every time you lower your training loss, you're going to increase your test loss, right? That sucks, right? So in fact, actually, for learning to be possible in some sense, we have to make assumptions, and those assumptions generally are in line with the way the world works. And that is that the training and the test data have to be related in some way. And the most common assumption is that they are, that the training and test data are identically distributed and independently distributed. So that this is abbreviated independent and identically distributed. In other words, they come from the same distribution. So label switches like this would be very, very, very uncommon, right? And they're independent. And this independent assumption we've already sort of talked about in the allergy and in the allergy case. That's more for just passing expectations through in the right way. So the idea.
Right. Do we need the ground truth labels for the test data set?
For the test data set, yes. For test data, the actual test data that's out there in the real world that you never actually see, you don't have them, right? So you do need the ground truth labels for the test data set. So your training and test data are independent and identically distributed if all the examples come from the same distribution. That's the identically distributed part, and these examples are sampled independently. In other words, the order doesn't matter, right? So in this person job income rating example that we saw a while ago, right? Row 1 comes from the same distributions as 2 and 3. Row 4 doesn't depend on the values of in rows 1 and 3. And if you're unfamiliar with this IID thing, right? So most of you will be familiar with decks of cards, right? So if you want to draw a sequence of cards in an IID way, one way to do it is you pick a card, you put it back in the deck, you reshuffle the deck, and you repeat, right? That's an IID draw. It's independent because you reshuffle in between every single time, and every time you pull out a card is going to be an independent draw, right? And they're identically distributed because the deck remains the same size, right? You have all 52 cards and you reshuffle it, and that's totally fine, right? If you pick a card and you put it back in the deck and you repeat, that's not IID, right? Because there's no shuffle in between, right? And certainly if you pick a card, and this one's more obvious, if you pick a card and you don't put it back, then you reshuffle and repeat. That's also not IID, that's sampling without replacement. That's distinctly not an IID draw. So we talked about this in the food allergy case. I think even in this in this course, right? Is the food allergy data IID? Do all the examples come from the same distribution? Does the order of the examples matter? You can argue no, right? I think fairly reasonably, right? Obviously, we already talked about the fact that like what you eat on the previous day can influence whether or not you get sick, right? So probably the rows, if they're collected on a day in and day out basis, are not actually independent. And your eating habits might change over time, right? So there might be a drift in the data, so they're not actually IID, right? So what do we do this? Well, we can just, and this is what we're going to do in this course, more or less, although it's not the only thing you can do. You just ignore the fact that the data is not actually IID, and you hope for the best, and you hope your model does okay anyway. The impact of it not being IID more or less means that your classifier might not do as well as it could. That's okay. Sometimes it's fine. Maybe you like stack features. You take features from the previous day and add them, like we talked about before. Or maybe you can put time as an additional feature, or you can change the model itself. So we'll dip our toe just a teeny bit in learning theory and say, like, why does the IID assumption make learning possible? So basically, patterns in the training examples are likely to be the same in the test examples. That's really at the crux of the matter. But the IID assumption is rarely true. It's a decent approximation. Yeah, there are other assumptions you can make. Learning theory is a big discipline, but basically it in general explores how training error is related to test error. So we're going to do a very simple thing using the following notation. So E-train here is the error on the training data, and E-test is the error on the testing data. So we're going to do some really simple math, my favorite kind of math, right? So we're going to start with this equation, E-test equals E-test, and then we're going to add and subtract E-train on the right. Okay, cool. Okay, that's it. I'm going to group those terms, and we're going to identify this thing over here, E-test is the test error, that's what it is, right? And this thing over here is the training error. Great, okay. The approximation error is this thing in the middle, this difference, right? So this is just basically a perspective. How does this perspective help? It helps you think about what's going on when you're with your models, right? So if this approximation error here is small, then the training error is a good approximation to the test error, right? So the question is, like, what does E approximation depend on, right? Well, for one, it tends to get smaller as N gets larger, as the number of samples gets larger, and it tends to grow as the model gets more complicated. Let's take a look at this, right? And we'll take a look at this from the following perspective. It kind of, this leads to a fundamental trade-off, like how small can you make the training error? And this is like traded off against how well the training error approximates the test error. So to be very concrete, like simple models like decision sums, E approximate is low by virtue of the fact that the test and training error are likely to be pretty close, right? But the training error might actually be pretty high. Complex models like deep decision trees and other models that we'll see later on in the course, the training error can be quite low, but the approximation error can be very high. In other words, it can be very sensitive to training data. So what do we see when we actually train models, right? And here we're going to talk about decision trees, like we've been talking about, because those are what we have in our toolbox right now, right? if we look at on the horizontal axis here, decision tree depth, and this is going to be errors of various kinds on the vertical axis, right? Then we can drive training error to 0 as we increase the decision tree depth, basically, right? Cool. So training error is high for low depth, and training error gets better with depth, right? And what we see over and over and over and over again is that test error initially will go down, right, as your model complexity increases or model expressivity increases, right? But then eventually it starts to increase this test error, right? And that's what we call overfitting, right? So you've overfit to a particular data set, which means that your generalization is not as good. And that generalization gap is captured with this E approximation concept. So, question that Payman asked before, how do we decide decision tree depth? We care about test error, we can't look at it, so what do we do? One answer, and this is a very common answer, is to use part of the training data to approximate the test error, right? So what do we do? We split the examples into a training set and what we call a validation set. And this is another, so now we've got training, validation, and test, right? So we train the model based on the validation test. We test the model based on the validation data, and then we go from there, okay? So X and Y are as before, we just split them, right? And this split, we're gonna see different variants of this split, so don't get too worried about exactly how we split it and what fractions and so on and so forth, like the question that came before. Just be aware that there's going to be a training data set and some validation data set, right? So step 1, you train the model using X train and Y train, right? Step 2, you predict using the model on X validate, right? This bit down here, and that gives you some Y hat, right? Step 3, you look at you basically look at the validation error, right? And that's what we do, right? And if the data are somehow ordered, the split should be random. That's a detail that isn't super important at this point. The critical part is that the validation error is an unbiased approximation of the test error, okay? So this is an expectation over data items drawn from the true data generation. And this is just almost trivial statement here, right? So we have the test error, expectation over IID samples, validation error, expectation over IID samples. Provided that you make the IID assumption, this expectation passes through, and this is just almost a tautology, right? The point is, like, if you have like, just to drive home the high level point, in the midterm case, if you have 2 practice midterms, basically you hide one away, put it in the closet, you don't think about it, and you practice and you really, really like work hard on the first midterm, and then you take the second one, right? That second one is probably a pretty good estimator of how you'll do on the real examination. Oh yeah, I see some questions popping up. That's good. We're running short on time, but Siddharth's question about would we overfit with the validation set as well? Absolutely. After performing many predictions with it, so we're going to be careful about that in the next couple of slides. And blood pressure rising, whomever that is. We're not going to talk about cross-validation today, but there are ways to do exactly what you're suggesting here, right? So we're going to use the validation error to choose what are hyperparameters. So here's another terminology. This is a little bit contentious. I don't particularly like this terminology, but we're going to go with it here. We're going to talk about parameters and hyperparameters in this course, okay? And in the decision tree case, the rule values, all of the rule values are called parameters, right? And the parameters are the things that we can fit using the training data. They control how well we fit a particular data set. So we train a model by trying to find the best parameters on the training data. The depth, for instance, of a decision tree, this again, we're just going from very concrete terms here, is called a hyperparameter. And the distinction between parameter and hyperparameter is subtle and largely arbitrary. But here, the distinction will be the things that we fit using the data set and the things that we don't, right? So in particular, in this course, hyperparameters will be like parameters that control how complex the model is, like, for instance, the depth of a decision tree. In some sense, we can't train a hyperparameter, right? In what we've seen so far, you can always fit the training data better by making the model more complicated. So what we can do is we can validate or choose amongst different hyperparameter values using a validation score. So yeah. So how do we choose hyperparameters as a validation set? Well, one way to do it is we try a depth 1 decision tree, we compute the validation error. Try a depth 2 decision tree, compute the validation error. Try depth 3 decision tree, compute the validation error, so on and so forth, right? And then you just return the depth with the lowest validation error, right? And to be clear, after you choose the hyperparameter that maximizes the validation error, or sorry, minimizes the validation error, basically you almost always retrain them, whatever model you're using the full training data set with the chosen hyperparameter. There's a little bit of a digression before we finish up, right? So another name for this overfitting is optimization bias. I'm not missing questions, am I, Damon?
Sorry?
I'm not missing questions, am I?
Would the number of features also be the hyperparameter? Yeah, you get this. Can we ternary search on the depths to find the best depth in logarithmic time?
Okay, so the first one is really, both of them are interesting questions, but the first one from Akim is really a super good question. Would the number of features also be a hyperparameter, right? I.e. how many choosing how many parameters to use? Yes, in the way we're talking about hyperparameters in this course, most definitely yes. And that's a really nice point that you brought up there. From Aishan, I guess, can we do ternary search on the depth to find the best depth in logarithmic time? Good question. I've never even thought about it. I'll have to take that one offline. If it's super important, we can address it. But that's something you can worry about. And then from Shaunak, but how can we choose how many features to use? That's going to come up throughout the course, right? Just imagine a situation in which you have a big bag full of features and you might want to start doing feature selection by adding features or computing more features or something like that. We're going to talk about this capacity control and choosing stuff. This is these are really good forward-looking questions for the rest of the course. And it's actually not a nice way to think about what's about to happen here, because like another way of what we've been talking about in terms of overfitting is just optimization bias, right? So the question is really like, relative to true test error, like how biased is an error that we optimize over many possibilities? And here we can think about the possibilities as being either a training phase or hyperparameter selection phase. Either one, we're going to look at lots of different models, right? So in the training phase, we're going to look at lots of different trees. In the hyperparameter selection thing, we're going to look at different depths of trees, for instance, and the cardinalities of these sets are going to be different for different models, and the characteristics of these sets are going to be different for different models, right? So if we want to look at optimization bias of parameter learning, like during learning, for instance, we could search over tons of different decision trees. We do, in fact. And that means that we can get lucky and find one out of all of these trees with very low training error by chance, right? So this is going to be overfitting of the training error. And just as suggested, right, if we look at the validation set, we can also, if we optimize over, a bunch of trees, right? In this particular case, a bunch of depths, you might find one of them has low validation error by chance. So this would be overfitting of the validation error, right?
What is a decision tree rule? Is it feature? I think someone asked me privately.
Say again?
What is a decision tree rule? Is it feature?
Decision tree rule is the feature, the value, the return values, the full thing, right? Yeah, and no, I thought we could. Okay, don't worry about feature selection, right? There's a we'll get there. That will come. but the point is that the structure, like you can think of hyperparameters as something that controls the structure of the model somehow, and parameters as something that's learnable within a particular structure. I think that's probably the nicest way to say it for this particular course. For a statistician, parameters and hyperparameters are exactly the same thing. Anyway, so let's talk about this optimization bias for just a second, where we're looking at lots of different possible models, right? And we'll do this again from some sort of concrete application perspective. So let's think about some sort of multiple choice test, right? This is going to be like our classification problem in some sense, right? It's got 10 questions. You can choose A, B, C, or D, right? So if you propose a model basically that chooses answers randomly, right? Then the expected grade on the test, like if you just like have a 10 question test and you choose answers randomly, right? The expected grade is 25%, right? There's no bias at all. You just like, that's what it is. But if your test taking model strategy or whatever, right, is to fill out a couple of tests randomly and then pick the best performing test, and the expected grade actually goes up, right? There's an optimization bias here. And if you keep doing this, right, if you like propose more and more models for this, right, the probability that you do well goes up quite a lot, right? So once you have a lot of chances to do very, very well, you kind of expect to do well. But then if you use the same system, as it were, on new questions, the random choice accuracy is still 25%, right? Okay. If instead we go from a 10 question test to a 100 question test, then the optimization bias still grows with the number of things we try, right? But the optimization bias shrinks quickly with the number of examples. So in other words, when we go from 10 to 100, right, the optimization bias goes down. So in other words, the number of training examples, optimization bias goes down, but it still goes up, okay? Particularly if you, in this case, overuse your validation set, as the question discussed. So we're okay on time today for a change, which is great. So let's wrap up with some summary, and then I'll take some questions. So we introduced the concept of training and testing error, right? What we care about in machine learning is the testing error, right? We introduced the golden rule of machine learning, and this is really, really important in that the test data cannot influence training the model in any way, okay? We also talked about this independent and identically distributed assumption that we make. And the really important part about this that makes learning possible is that the test, training, and validation data, all the data that we get, is assumed to come from the same data generating process, right? And that's what makes learning possible, because there's similarity between the examples in the test and training sets, right? If there weren't, then all bets are off, right? There is a fundamental trade-off, and this is like kind of the main concept that amongst all of these, they're all main concepts that you want to get, but these main concepts that you want to get include the fundamental trade-off, which is to say that you can always drive the training error down to zero with almost any model family we're going to talk about. But driving the training error down to zero does not actually lead necessarily, and in fact, in most cases, does not lead to good generalization. So yeah, there's a trade-off between getting low training error and having the training error approximate the actual true test error, right? And when we're going to do hyperparameter selection, basically, we're going to need to be able to query the test error several times in some sense, right? And the way we do that is to keep a validation set around so we can use it to approximate the test error. And we've introduced this concept, and I've probably polluted you with statistical truth too much when I was talking about it, but I've introduced this concept of parameter versus hyperparameter. So hyperparameters are parameters that control model complexity in some sense. And here we're talking about tree depth, or so the questions have hinted at, and these are very good hints, but they'll be very confusing right now. Just hold them in your head for a little while. They're like the number of features that you have, and these sorts of things are hyperparameters that you can control, and usually set those with a validation set. So next time, whoa, that's awesome. Next time we'll talk about the best machine learning method, and I'll stick around until 5 for questions. Thank you very much. Okay. So, Shaunak, oh, I think I got that one. So Tobias, right? Is one of the reasons people use random forest rather than basic decision trees, this optimization error problem. The short answer to that is yes. The longer answer is that whatever classifier, regressor, or whatever you use, it should match in some heinously difficult to describe in this setting way the data generating process. So in the allergy example, for instance, I can tell you exactly the quantities of each of these things that are going to cause me to get sick or not, right? And if whatever model family you have is capable of exactly expressing that conditional relationship, then you're golden, right? So maybe random forests are better, maybe decision trees are better, maybe support vector machines are better, maybe neural networks are better. There's an inductive bias that comes from the structure of the model that you are considering, and if and only if the true data generating process is aligned with the inductive bias of the model that you're using, will you have really, really good generalization performance. So the question of, is this one of the reasons why people use random forests? The reason why people use random forests is that random forests tend to generalize well, which suggests that the inductive bias in random forests is compatible with the data generating process for lots and lots of kinds of data. That's a very difficult answer to consume at this point, but it's pretty close to the truth. When there are multiple hyperparameters, we can't tune each independently, right? If not, doesn't it become an NP-hard problem? Okay, Fisher, this is an awesome question. So let's remove the NP-hard part of it for a second and say that if we have lots and lots of hyperparameters, then we have an interesting problem of needing to evaluate or estimate the test error using validation, using a validation set many times, which is going to lead to overfitting of the validation set, so on and so forth. So multiple hyperparameters is not in and of itself such a problem, but fitting to the overfitting to the validation set is the problem that we're trying to stress right now. Computationally, all of the problems that we're talking about, right, so far, are combinatorial optimization problems, which means that their solution will take exponential time, which means that they're reducible to the NP-hard set of problems. So, so yes, multiple hyperparameters selection, if they're discrete hyperparameters, they need not be discrete hyperparameters, results in a combinatorial optimization problem, which results in exponential complexity, which results into reducibility. But that's a long-winded answer to a relatively simple question. But I think that should make a case. I don't even know what Discord is. What's Discord?
Yeah, I'm not sure.
It's like Slack.
That's what Piazza is. That's UBC's privacy preserving proper communication channel. So that's it. Any other questions? You're all welcome, obviously. How come they don't call them meta parameters instead? Some people do, actually, not very many. It's just what they're called, hyperparameters, by the set of people who distinguish between hyperparameters and parameters. They're called hyperparameters. At 98 F1 on Piazza, of course. Yeah, I don't know, but Ramon, that's a good question. Carl Friston's free energy. I could talk about variational inference and amortized inference. Those are as close as I'm going to get to Carl Friston's free energy thing.
What about in 540?
Since these lectures might be released to the public someday, I'm going to abstain from making any public.
Okay. All right, sorry.
Could you give an example on how test data can influence training the model? It cannot, unless you're cheating. But I mean, hello. If I gave you the final examination for the course and all of its answers, the way you would prepare for that examination would be A, to memorize those questions and answers, and that's it. Why would you do anything else, right? So your model of what you need to learn for the course and your ability to generalize beyond what's in the final examination would be severely, like while you're training, why would you focus any attention on anything other than just memorizing those final examination question answers? If foreigners who never live in the US were to do an analysis of, don't they have to rely on optimization bias of parameter learning because they don't know that San Francisco is more hilly? Sorry, Sol, I apologize for using a US example. If that's the real basis of this question. The point of that example was very simply to show that, just to reiterate how decision trees would be learned. The fact that we chose that as a particular feature, or that it might be automatically chosen, is that's just what it is. Your existing decision tree algorithm would choose features in whichever way, and that has nothing to do with optimization bias. The fact that you might choose to fit the data perfectly with a very, very deep tree, that would lead to optimization bias. It has nothing to do with where the data comes from or the particular nationality of the person doing the optimization. Anything else? Okay, cool. Thank you all for your time.
Thank you.
See you on Friday, Payman. Appreciate it.